Hey guys, welcome back. We're starting chapter 2 of linear algebra. This is a great chapter. In this chapter, we're going to be discussing matrices. In section 2.1, we're going to be talking about operations with matrices, which is pretty much what we're doing in this video. Some of the properties of matrix operations. We're going to talk about the inverse of a matrix, which is extremely important. We're going to be talking about elementary matrices, Markov chains, and more applications of matrix operations. You're going to be able to see when you're done with this chapter where matrices are so useful in everyday lives, in everyday situations. I do not know why I had these emojis, but I just wanted to make it fun. All right, so what are we going to do in this section? In the first section, and not all of this is going to be on this video, I'm going to try to make the videos as short as possible so that way that you can watch them in pieces. So in the first section, we're going to determine whether two matrices are equal. That's going to be pretty easy, but I want you guys to look out for the notations. We're going to also add and subtract matrices and multiply matrix by scalars, and we're going to multiply two matrices. We're also going to use matrices to solve a system of linear equation, which is in a later video, and then the partition of a matrix and write a linear combination of column vectors. This part here is so important. Now, I know I spoke really quickly, so just pause and take a look at it if you want to. I'll go slower here. So first, we're going to determine whether two matrices are equal. Okay, fundamentals of matrix theory. An uppercase letter, such as capital A, B, or C, a representative element enclosed in brackets, such as what I have here and here, and a rectangular array of numbers. These are all conventional ways of discussing a matrix. So we can have this big capital letter A. Okay, let me get a black pen. We can get this big capital letter A to discuss a matrix, and that would pretty much be equal to sort of an array of numbers. When you have something like this in a bracket, it's very, very important to recognize that this is going to be a single element. So we can say, oh, that's 7. So if you have B1, 2, and I say that's equal to 7, that means if you have a matrix B, take a look at the first row, second column. So you're talking about that person there is a 7. So that's what this means here, okay? So this is a single element. These are big matrix. And then we have our rectangular array, which we've had since chapter 1. Okay? So what is the definition of equality of matrices? Well, two matrices are equal when they have the same size and the same element in each row and column. That makes sense. If it looks the same, then they're equal. So let's take a look at this notation here. This is A, representing an array of a matrix that has a rectangular array, and there's all these elements in them. B is similar, and they need to have the same m by n size, and every single number that's in A needs to be in B in the same location. Okay? This is for a row, and this is for a column. So what this notation is telling us is basically for every single row and column, ij, both of them have to be the same, and they have to be the same size. So in this here, matrices A and B are not equal. That's obvious. They have the same numbers, but first and foremost, they don't even have the same size. A is 1 row by 2 columns. B is 2 rows by 1 column. So right away, they're not equal. Here, A and B will be equal. Okay, 1, 2, 3, 4. It is equal to B only if x equals 3. And the point of this, I know, seems very basic, but you're going to have to solve for x and y and z and so on. So it's important to know. A matrix that has only one column is called a column matrix or a column vector. Therefore, in this example, B is called a column vector or a column matrix. I prefer to call it a column vector, but that's for linear independence, which is later on. So please do not let these little subtle sentences, statements just don't just read it and walk away from it. Say, okay, column, vector, column, matrix. Got it. All right. So, very important. Boldface lowercase letters often designate column matrices and row matrices. This is very important. So we have this A is equal to 1, 2, 3, 4. You can refer to 1, 3 with this boldface lowercase letter, A1, and we can do the same thing for A2, 2, 4. Okay? So matrix A is partitioned into two columns, A1, A2. It will be, and when you read it, be careful, bold, and it'll be lowercase. That typically refers to a column. Okay. Okay, let's just do this one and then I'll stop the video, okay? Definition of a matrix addition. If matrix A and matrix B are of the same size m by n, then their sum is going to have that same size. And the way that you add them is pretty much whatever is in row 1, column 1 of A gets added to row 1, column 1 of B. If their sizes are different, you cannot add them. So we say it's undefined. So in this case, the only thing that we could add is A and B. Is the only thing that you could add. Because this is a 2 by 2 and because this is a 2 by 2, then what's going to happen here is you're going to get a 2 by 2. I love to do this and I love to fill in the numbers. So let's say you wanted this number here. Then you go here and you add them. If you want this number here, then you go here and you add them. The way that I prefer to do it is I say, okay, I want the first row, second column. So I go to my first row, second column, first row, second column, and I add them. I know it seems tedious, but that's how you do it. So you have to have the same dimensions in order to add them. In the next video, we'll talk about scalar and multiplication. So come